Thanks, organizer, for inviting me to give the talk. So I'll talk about extension beyond cold dark matter. Though Lambda CDM has been a very standard cosmological model, but if you talk to particle physicists, it is very non-standard, okay? Because neither we know what Lambda is and neither we know what cold dark matter is because we have not detected. So the search for dark matter is basically driven by guesswork, because you need to know what it interacts with and then you build detector. And one such guess was WIMP miracle. It was not only a guess, but there was some sort of coincidence. And as we all know that WIMP were very heavy particle and they were annihilating to standard model particle and back and forth. And as the universe cools down, only the annihilation was going to the standard model particle because there was not enough energy to create back WIMPs. And at some point, Hubble expansion took over. And the annihilation rate basically tells you how much relic dark matter you have. And that exactly matched with the supersymmetric particle and they were designed to explain the Higgs mass. So it was not designed to explain the dark matter, but at the same time you were getting that. So that's the basic idea of WIMP miracle. And the last 20 years of dark matter search has been driven by the detection principle of this direct detection of WIMP, and also the other result from LHC and indirect search from a satellite experiment. And at the present, given the Higgs mass and the non-detection of dark matter in collider, basically tells you that it is not so much of a miracle anymore, because you don't get naturally the cosmic density. And at the same time, as you know, these are all exclusion plots of different dark matter search. The below one are not yet in the game, but up to Xenon 1T, the upper part is ruled out. So around 20% of the preferred parameter space of dark matter, supersymmetric dark matter is already ruled out. And the main problem here is there are some experiment called DAMA. They have claimed that they have detected dark matter with 8 or 9 sigma, lies on the wrong side of the exclusion bound from Xenon. So if it would be on the below, then it will be a dark matter discovery. But where they lie is actually excluded from Xenon with a huge sigma. So that's why it is very much complicated, and given this non-detection of dark matter and also given astrophysical anomalies, I'll not go into the detail, because in small scale, WIMP is also not doing that great because it has some problem, as you know, satellite problem and too big to fail problem. There are many. So there is a good point to look for cosmology, look in cosmology, that what cosmology is telling us about dark matter. Maybe we are looking in the wrong place, our guesswork is wrong. And I feel that the cosmology in the next few years is going to shed a huge amount of information, the light into the dark matter search. So the main thing in cosmology is inflation gives us this power spectra. And what cosmology does is when universe enters to matter-dominated era, because of transition from radiation to matter, as you know, the power spectra changes. Now, if you change the dark matter physics from WIMP, you are not allowed to do anything in the large scale, because that's where the Planck is quite okay with CDM. So if you have to go beyond CDM, you have to look for fluctuation, look for change from which CDM predicts in the small scale. And that's where your Lyman alpha is here, and then 21 centimeter physics is coming, and that's where, and you know that as that's the reason from the constant on neutrino mass just came by looking into the deviation in matter power spectra, and the constant we get is much stranger than the particle physics constant. So that's why the cosmology is coming into the game, where it is giving a lot of constant on the particle physics. So today I'll just focus on couple of 2-3 main philosophies where you want to deviate from CDM. First philosophy is you bring down the mass of cold dark matter from GeV to keV sterile neutrino, and as the mass comes down, it has more velocity, and you free stream a lot, and then you erase the structure, and then you suppress. But there are problems with warm dark matter because it has huge constant from Lyman alpha, and also the particle physics wise, it is not that attractive. So there are recently in the literature or recently in this beyond CDM game, there has been few ideas. The first idea is, you have heard about it, fuzzy dark matter, or because here you get to, the lowest you can get is the keV range. But if you move to scalar field, you can go down to 10 to the power minus 22 electron volt, which is much below than neutrino mass. But still, you predict you are okay with the cosmological data. So I'll just tell how this works, and then I'll again come back. So this work is basically, you have a scalar field like axion, and the main idea here is the Hubble friction and the mass, they compete. When Hubble friction is too much, they behave like cosmological constant. And when the Hubble friction goes down as the universe expands, this term dominates, and you have a coherent oscillations, and which exactly behave like a dark matter. So that's why if you just do this comparison, that H goes as like T square over M Planck in radiation dominated era, and you match it with MA, and you will get this mass. So this is way below than a fermionic mass, which is keV. And the good thing is, in this mass range, the de Broglie wavelength actually kiloparsec, and you get a quantum pressure below that. So that's why you don't allow the structure to grow. So that's why this mass range basically also try to solve the small scale issues of the cold dark matter. But there are other mechanisms which is driven by new physics, can be possible. And one such mechanism is called late forming dark matter, which I have been part of. And another is recently is called ballistic dark matter. There is a talk on that on 25th. So what happens here is a phase transition. So radiation component with equation of state 1/3 transits into equation of state 0. And depending on the mechanism of transition, you can have the radiation component having its velocity perturbation and density perturbation, and it map suddenly into cold dark matter. And that can have, in ballistic dark matter, there will be talk on that, you can actually change the CMB peaks also. And for LFDM, it is mainly the matter power spectra. But depending on the mechanism, both LFDM and ballistic dark matter get constant from reionization physics. So that I will be telling a little bit. And another option is, okay, you don't want to let go of the cold dark matter, so then you keep it, but then you allow interaction with like a photon-like particle in dark sector. So then you basically again get similar thing, which I'll tell. If you allow this kind of interactions in the dark sector, then you get similar to baryon photon oscillations in the dark sector. And because of that, you also suppress the power because you get a pressure. So in axion case, it is the quantum pressure because of the de Broglie wavelength case, and in this case, it is the basically dark radiation drags the dark matter particle. And there has been a lot of work, it's called ethos formalism, that if in many particle physics model, you can allow dark matter to interact with the light particle, and so in all these cases, you get suppressed power, and you get a specific features, is called dark acoustic oscillations, either in ballistic dark matter or in late forming dark matter, or in these cases, you get these oscillations. Now the question is whether you can detect them or not. The answer is no, through linear physics, so through nonlinear physics, because if you put them in your n-body simulation and you look for your present day matter power spectra, nonlinear matter power spectra, they erases the oscillations because it's smoothed out. So this was a simulation done in Pierre Stefano group in Paris, and they say like you cannot see them. So the only option here is somehow if you go to early time where the nonlinearity is less. And the thing is, in all the model we are considering late forming dark matter and ethos, they are quite okay with Planck. So Planck will not distinguish between cold dark matter or all these dark matter model. So only chance is if you probe not so nonlinearism, and that is the idea, that is the epoch of reionization, because that time whether you can probe that, and the 21 centimeter brightness power spectra is a possibility. So I'll just tell that what happens in the epoch of reionization, you have your early halo mass function. This is also a nonlinear simulation. You start with say redshift 200 and evolve it to redshift 8 or 9. And here, when you deviate from cold dark matter, if you talk to n-body people, I'm not an expert in that, there are a lot of controversies. So people say that you predict, so you get some spurious halos here. So this is actual function from lambda CDM when you move to all other different kind of dark matter. But the main thing here is, even if you take the spurious halos, there has been some group who take care of the spurious, then you actually come down. Even you reduce more power. So even if you take this kind of halo mass function and put a constant, you are still giving a conservative constant, because later if you have more handle over this halo mass function, then your constant will be stranger. So now once you have a halo mass function, then from there you can go from structure to reionization. And there one parameter, because these are the halos, and then there are few parameter goes into the game which are highly non-constant. Those are like the escape fraction, because you know that the star formation happens and not all the photons will escape. And then the star formation rate, escape fraction, and then there is a proportionality constant which basically called n-ion baryon, and all these parameters can be taken into like an n-ion. And this is an unknown parameter. We don't know that much from the astrophysics. But if you look into the literature for many models, roughly you can say that you can assume that this is less than 500. If you cross this 500, then for POP3 star, it can be more, but we know that the POP3 stars cannot reionize the universe because their lifetime is in million years. So safely, if you assume that this is 500 less than, and then you demand, then you have to match your optical depth from Planck, and we demand that a pivot point of reionization, that x equal at z is equal to 8, we demand 0.5 ionization fraction. You can change that, then that will change your constant also. But this is a good assumption, because given the history of reionization, we don't know that much, but with the Planck optical depth and we know that at z is equal to 6, reionization is complete. So at z is equal to 8.5 is a good number. And then you use excursion set mechanism. It's a code developed in Somnath Bharadwaj's group and given and also input from Tirthankar. They are in the audience. So with that, you run the for different values of n-ion. You claim that I have at z is equal to 8, I claim 0.5 ionization fraction. Then you see that as you go to beyond standard model of dark matter, cold dark matter, you have to increase n-ion to get your reionization 0.5 at z is equal to 8, and at some point they cross 500. Then you can say that then you cannot achieve reionization at z is equal to 8 with those model, and that constrains your particle physics model. And with that, we have basically told, we have given this constant that for fuzzy dark matter, it has to be 10 to the power minus 3 times more than that. For late forming dark matter has to form, even it is true for ballistic dark matter, it has to form before 4 into 10 to the power 5 redshift. So if it forms later, then you will not get good reionization with a natural value of n-ion. And for ethos, for WIMP interacting with radiation, you can give a constant on the particle physics parameter, which is given by A4, which basically tells that how much is the strength of interaction between dark radiation and dark matter. And these are all good constant in the boundary. And the main thing is, if you go to the power spectra, the good news is all this suppressed power actually enhances your 21 centimeter power spectra. So if we measure the future experiment in SCA or other experiment which are coming, first you will hit non-standard dark matter. So it is easy to rule them out compared to CDM. So that's a good news in this going beyond lambda CDM. And these are the model which also solves your small scale issues of lambda. So in some way, in 21 centimeter is going to either rule them out or will give a sign that we are seeing the sign of suppressed oscillations in the initial time when the universe was radiation dominated, and dark matter is not so simple like WIMP. Maybe it has more physics. So that's why I feel that 21 centimeter can be a very interesting regime to probe this kind of dark matter, given that we didn't see the cold dark matter for the last 20 years. Okay, so I'll just stop here. Yeah.
Questions?
Yeah.
Andrea, the mic there.
A very interesting study, but I would like to warn you that the devil is in the details. So practically all those kind of studies, they're limited by our ignorance on the baryonic side of the physics. For example, you not only have to assume how many photons are produced, but you also have to assume how many escape. Those two numbers can be mass dependent and redshift dependent.
Yeah.
And when you try to fold in all those things, you see that all those naive limits that you can take, assuming a single number, they get very fuzzy.
Yeah.
So I think at the moment we are still in the dark, in the sense that the baryonic physics is what limits our understanding of the dark sector.
Yeah. But if we can somehow come up with a conservative bound, if we have some idea that, not going into the details, but maybe some number which will tell her that this is very unnatural number, then, but I don't know, but maybe that also in dark. We don't know that what is the value of all this.
I think our ignorance is such that we don't know what is unnatural in this field yet.
Anirban?
Yeah.
Okay, I would like to ask two questions. One is that how you can break the degeneracy between the small scale suppression, because you can explain this with the neutrino mass, increasing the neutrino mass. So how?
So because you have a constant from neutrino mass from Planck, so that kind of neutrino mass will not give this kind of suppression. So that's why neutrino mass is not in the game in this model, because neutrino mass is constant from Planck data. Yeah.
Okay, and another thing is when you are considering the source of reionization, so how these different sources are balancing and contributing in the total the ionization fraction. So it can, something can be ionized from the star forming galaxies.
The star formation is the main source. We didn't assume any other, because the halo forms and the star formation from the halo with an anion, which takes care of all the astrophysics basically. So no other sources.
No quasars.
No quasars, nothing.
Okay.
Yeah.
Thank you.
Okay.
Thanks, Subinoy, again, and end this session.